Morning. I'm Dr. K. Raghuram Mohan Reddy. The course name is Unconventional Machining Process. Today's topic is Electrodischarge Machining. Under this, I'm going to cover electrode materials. Right. So, electrode discharge machining and electrode materials is the today's topic under unconventional machining process. These two are the course outcomes. At the end of this session, student will be able to list the different electrode materials and its characteristics. The second one is understand the electrode wear mechanism. Okay, so in the coming lecture, we will see the wear mechanism of workpiece. Okay, right. Okay, as usually under non-traditional machining process, we have three types, basic types: mechanical, thermal, chemical and electrochemical. These three are the three broad classification of non-traditional machining process. Again, under each category, we have different non-traditional machining processes. Okay, under mechanical, already we have discussed ultrasonic machining, water jet machining, abrasive water jet machining, ice jet machining. Okay, right. Under thermal, we are discussing electrical discharge machining or electrodischarge machining. Right. This is the schematic working principle of electrodischarge machining. So here the workpiece is fixed to the fixture which is located on the table. Okay, and the tool is connected to servo control feed mechanism. Okay, the tool holder holds the tool. Okay, the tool holder is connected to servo control feed mechanism or the feeding, and it is negative electrode. Okay, the workpiece is considered to be a positive electrode, that is nothing but anode, and the workpiece is cathode. Okay, and the two electrodes, workpiece and the tool, are immersed in the dielectric fluid medium. Okay, so the dielectric fluid medium circulates between the tool and the workpiece while the tool is having a feed mechanism. Okay, right. Here the workpiece will move in X, Y and Z directions in order to cut different profiles, X, Y, Z directions. Okay, right. Regarding dielectric fluid medium, the dielectric fluid medium circulates through pump, and the dielectric fluid medium is constantly filtered. Why? Because during machining, the removal of both workpiece and electrode material should not again mix with dielectric fluid medium. That debris we have to filter. Right. Here you can observe the gap between workpiece and electrode. Okay, so with the specified gap and DC pulse generator supply, spark or an arc will create, and that arc strikes the workpiece through this dielectric fluid medium. Okay, so this is about schematic working of electrical discharge machining. Right, here we can see this is anode workpiece, this is cathode, and power supply is given. Okay, when this cathode, that is nothing but tool, will come near to anode, that is workpiece, spark will generate. Okay, so with this specified gap, the spark will generate. Okay, so this cathode is the tool material, this anode is the workpiece material. So this is tool, this is workpiece. So tool will fed towards the workpiece, so that when there is a specified gap between anode and cathode, the spark will generate, and that spark strike the workpiece, so that the material removal will take place. However, the material removal not only from the anode, okay, but also from cathode, it will take place. Now today we are discussing that cathode material, that is electrode material. Okay, right. Other names of electrical discharge machining. However, we have already discussed that this is a predominant non-conventional machining process, comes under thermal category. Okay, which is used for very hard and brittle materials, which cannot be possible by means of other conventional machining process. Right. So these four are the other names of electrical discharge machining. The first one is spark eroding, spark machining, wire erosion. Fourth one is wire burning. Okay, let me repeat. The other names of electrical discharge machining are spark eroding, spark machining, wire erosion, wire burning. Okay, right. Let us brief about the history of electrical discharge machining. Right. The history of electro-discharge machining dates back to the days of World War I and World War II, when BR and NI Lazarenko invented the relaxation circuit, that is RC. Okay, so which is very much important. Now the electrical discharge machining is working with this RC, relaxation circuit. Using a simple servo control, they maintain the gap width between the tool and the workpiece, reduced arcing, and made EDM more profitable. Okay, so already we have discussed that there must be a gap between tool and the workpiece in order to have the spark. Okay, when the electrical supply is on. Right. Evolution of EDM. Since 1940, die sinking by electrical discharge machining has been refined using pulse generators. Second one is planetary and orbital motion techniques, computer numerical control, adaptive control system. Now let me repeat. Die-sinking by electrical discharge machining has been refined using first one, pulse generators, second one, planetary and orbital motion techniques, third one, computer numerical control, fourth one, adaptive control systems. Okay, so here computer numerical control systems are that it is developed with the code in terms of numbers, alphabets and other special characters. Okay, right. During the 1960s, the extensive research led the progress of EDM when numerous problems related to mathematical modeling were tackled. Okay. However, for this mathematical modeling, the CAD approach, computer aided design, in order to make different features with different curvatures, it is required to develop a CAD model, computer aided design model. Okay, so Bezier spline surface or some other B-spline surfaces are to be created with this CAD model using this mathematical model approach. Okay, right. For regular shapes like cylinder, spherical, prismatic, no issue. But in order to have complex contours, shapes, we have to go with CAD and CAM. Okay, computer aided design and computer aided manufacturing. Under that, computer numerical control will play the basic role to run CAD and CAM. Okay, right. Evolution of wire idiom. Okay, let us discuss in brief. Okay, so in later stages, so we can discuss wire idiom in detail. Right. The evolution of wire idiom in the 1970s was due to the powerful generators, new wire tool electrodes, improved machine intelligence, and better flushing. Okay, so here wire idiom is now an emerging equipment for the machining of different contours. We will see in detail in later stages. Recently, the machining speed has gone up to 20 times, which has decreased machining costs by at least 30% and improved the surface finish by a factor 15. See how best the surface finish has been improved to 15 times. Okay, and the machining time has been reduced to 30%. Okay, right. So this is the significance and importance of wire idiom. Let us discuss in detail. This is the extension of electrical discharge machining. Okay, right. Next, EDM advantages. EDM has the following advantages. Number one, cavities with thin walls and fine features can be produced. See, usually we cannot produce thin walls and fine features with other conventional machining processes when the materials are hard and brittle, so that we have to use the electrical discharge machining. So that is the chief advantage of this electrical discharge machining. Second one, difficult geometry is possible. So when there is a complex geometry of shapes to be manufactured, other machining processes cannot produce. So we have to go with non-conventional electrical discharge machining process. However, the other machining, non-traditional machining processes are also there, but by this time we can say electrical discharge machining is apt for the complex geometries. Okay, right. The use of EDM is not affected by the hardness of the work material. So usually for conventional machining process, we have to choose the appropriate tools and need to maintain different machining conditions when the material is having hardness. So when the hardness is increasing, we have to take care when we are using traditional machining process. But here it is not like that. Whatever it may be the hardness, electrical discharge machining can be used to cut the material. Right. The process is burr free. Okay. At the end of the machining process, there will not be any burrs. Okay. So after machining and during machining, the dielectric fluid medium continuously circulates and the dielectric fluid medium flushes away the burrs. Okay. Right. Now let us see the EDM, electrodes and materials. Right. Metals with a high melting point and good electrical conductivity are usually chosen as tool materials for electrical discharge machining. Okay. So here both the workpiece and the electrode must have electrically conductive materials. Okay. And it has high melting point. Okay. Metals with a high melting point and good electrical conductivity are usually chosen as tool materials for electrical discharge machining. Okay. One is high melting point. The second one is electrical conductivity. Okay. These two are very much important for the electrode materials. Right. Now let us see the different materials. Out of all these materials, the graphite is the most common electrode material since it has fair wear characteristics and is easily machinable, and small flush holes can be drilled into graphite electrodes. Okay. It is a form of carbon, so that it has good wear resistance characteristics. Okay. Next, copper has good electrical discharge machining, wear and better conductivity. So after graphite, copper is the next good material for electrical discharge machining. It is usually used for better finishes in the range of 0.5 microns surface finish. Okay, so that is the significance of this copper electrode material. Right. Next, copper, tungsten and silver tungsten are used for making deep slots under poor flushing conditions, especially in tungsten carbides. Okay, tungsten carbides, WC. Okay, copper tungsten and silver tungsten are used for making deep slots under poor flushing conditions, especially in tungsten carbides. Okay, right. Third one, copper offers high machining rates as well as low electrode wear. Okay, so here copper offers high machining rates. So here machining rate is important parameter. Okay, high machining rate and low electrode wear. So here electrode should not be subjected to much wear. Okay, so for this copper is a good electrode material. Right. Already we have seen about graphite, that is the first electrode material. Next, copper. Now let us see copper graphite. Copper graphite is good for cross-sectional electrodes. It has better electrical conductivity than graphite, while the corner wear is higher. We'll see what is corner wear and all these things. But however, we'll come to conclude that copper graphite is better electrical conductivity than only graphite. Okay, so that it has some other good characteristics when compared to copper and graphite individually. Okay, we will see all these corner wear and the other ratios we will see in the coming slides. Right. Next one, brass. Ensures stable sparking conditions and is normally used for specialized applications such as drilling of small holes where the high electrode wear is acceptable. Okay, next material is brass. Okay, copper plus zinc. Okay, right. The reference is Metals Handbook 1989. Okay, right. Regarding electrode movements, in addition to the servo control feed, the tool electrode may have an additional rotary or orbiting motion. Usually for feeding, already discussed, servo controlled mechanism has been adopted. Along with this, the electrode may have an additional rotary or arbitrary motion. Okay, right. Electrode rotation helps to solve the flushing difficulty encountered when machining small holes with EDM. Okay, see, usually when it has a linear feed, okay, vertical feed, it digs but having a difficulty to remove the material. Okay, when the tool rotates like a drilling bit to solve the flushing difficulty. Okay, so here electrode rotation. Okay, when the electrode rotates, it can remove the debris or remove workpiece material easily from the hole or any slot. Okay, right. Next, electrode parameters. In addition to the increasing cutting speed, the quality of the hole produced is superior to that obtained using a stationary electrode. Okay, so here the quality depends on the working condition of the electrode. Okay, so if we use stationary electrode, we have one kind of quality, and we have superior quality when the cutting speed increases. Okay, when it has a rotary motion. Okay, see here, in addition to the increase in cutting speed, the quality of the hole produced is superior to that obtained using a stationary electrode. Okay, right. Electrode orbiting produces cavities having the shape of the electrode. Okay, similar to ultrasonic machining, here the cavity will be produced similar to that of the shape of the electrode. Okay, right. Electrode orbiting produces cavities having the shape of the electrode. Okay, suppose if we have electrode shape like this, okay, the similar cavity will be produced in the workpiece. Okay, so this is the tool edge or tip. Okay, the same cavity will be produced in the workpiece material. Right. The size of the electrode and radius of the orbit determine the size of the cavities. Okay, usually that is 2.54 mm maximum. Okay, the size of the electrode and the radius of the orbit. Okay, how much? Maximum 2.54 millimeters. Determine the size of the cavities. Next, electrode orbiting improves flushing by creating pumping effect of the dielectric liquid through the gap. Here, the pump supplies and the filters the dielectric fluid medium, and usually the pump increases the velocity of the circulating dielectric fluid. So along with that, the electrode orbiting setup improves the flushing by creating a pumping effect of the dielectric liquid through the gap. Okay, right. Now let us see the polarity of the electrode material. Right, here the polarity depends on both the workpiece and the electrode materials. Okay, we will see in detail, okay, the polarity of different electrode materials and workpiece materials. Okay. Now from this table, let us see the different workpiece materials. See here, this is workpiece material, this is electrode material. Okay. So electrode materials are graphite, copper, tungsten, steel, brass. Now let us see workpiece materials: steel, tungsten carbide, copper, aluminum, nickel base alloys. Okay. Now let us focus on copper and aluminum. Okay. So whatever it may be the electrode material, it means copper, graphite, copper, tungsten, steel, brass. Okay. When the workpiece material is aluminum, the polarity for all the materials is positive except for steel. For steel only it is negative. Okay. Understood? Okay. The combination of aluminum workpiece material and the other electrode materials will give positive polarity except for the steel. Okay. Right. Now let us come to copper as the workpiece material. Okay. So here different electrode materials, the polarity is negative. Okay. Okay. Right. Right. For steel, it has positive and negative polarity. Okay. And for copper, it is positive polarity. Copper tungsten, it is, for steel, it is positive and negative. For brass, it is negative. Okay. Now, when we take tungsten carbide as the workpiece material, for graphite, it is negative polarity. For copper, it has positive and negative polarity. For copper and tungsten, it has positive and negative polarity. For tungsten and steel, it has positive polarity. For tungsten and brass, it has negative polarity. Right. When come to nickel base alloys, almost similar polarities: positive, negative, positive, positive, negative, negative. Okay. So these polarities will play an important role at the time of generating sparks. Right. Now let us see types of electrode wear in electrical discharge machining. Okay. Now let us understand the nomenclature of tool electrode. Right. See, it has usually a prismatic shape. Okay. Up to this dotted line. Okay. Now this is called initial shape. Okay. That is called initial shape. So after making a smooth surface finish, that is called final shape. See how the final shape will be. Okay. Now this is called corner wear, LC. Okay, this is called corner wear. Okay, this is called side wear. Okay, and this is called end wear. Okay, so here corner wear, okay, side wear and end wear. Okay, okay, that is about tool electrode. Now when come to this workpiece, machined depth, capital D. Okay, so corner wear is represented with LC, side wear represented with LS, end wear represented with LE. Okay, machined depth is capital D. Right. Now let us see the same. Okay, and we'll see the ratios. Corner wear ratio. Okay, here the ratio depends on both the workpiece and electrode. Okay, right. Corner wear ratio is the ratio of, right, the corner wear ratio is the ratio of machined depth, capital D, to the corner wear, LC. Okay, D by LC. Right. Side wear ratio, that is the ratio of machined depth, capital D, to the side wear, LS. Okay. Third one, end wear ratio. It is the ratio of machined depth to the end wear, LE. So along with this, volume wear ratio, that is the ratio of volume of the workpiece removed to the volume of electrode consumed. Okay, right, that is VW by VE. Right. Okay, right. So this is figure 3, which is giving information about corner wear ratio, side wear ratio, end wear ratio and volume wear ratio. Right. The melting point is the most important factor in determining the tool wear. Okay, already we have discussed that melting point and electrical conductivity are the two important factors or parameters of the electrode material, out of which let us discuss the melting point. The melting point is the most important factor in determining the tool wear. Right. Electrode wear ratios are expressed as end wear, side wear, corner wear and volume wear as shown in figure 3. Already we have seen. Okay, from this we have already discussed. Okay, right. The term nowhere EDM occurs when electrode to workpiece wear ratio is 1% or less. Okay, so nowhere electrical discharge machining occurs when the electrode to workpiece wear ratio is 1% or less. Okay, so it is possible or not possible, we will see. Okay, right. Electrode wear depends on a number of factors associated with the EDM like voltage, current, electrode material and polarity. Okay, voltage, current, electrode material. Already we have seen different electrode materials like copper, graphite, brass, steel, copper, tungsten, etc. Okay, and different polarities, positive polarity and negative polarity. Okay, so these are the different factors associated to electrode wear. Right. Electrode shape effect. Shape also we have some effect on wear. Right. The change in shape of the tool electrode due to the electrode wear causes defects in the workpiece shape. Okay. Right. Electrode wear has even more pronounced effects when it comes to micro machining applications. Okay, so these two are the shape effects of the electrode. Now, let us see one more time. The corner wear ratio D by LC, side wear ratio D by LS, end wear ratio D by LE, volume wear ratio VW by VE. Okay, again we'll discuss further the various corner wear ratios for different electrode materials. See here, silver, tungsten and at the end aluminium. Okay, so these are the electrode materials in x-axis and in y-axis it is corner wear ratio percentage. Okay, so for different materials how the corner wear ratio is varying. Okay, it is very less for silver, tungsten and it is very high for aluminium. Okay, here the plus and minus are representing the polarity. Okay, that is plus represents positive polarity. Okay, and the minus represents the negative polarity. Okay, right. The low melting point of aluminium is associated with the highest wear ratio. Okay, see here for aluminium the wear ratio is highest. Okay, right. Graphite has shown a low tendency to wear and has the possibility of being molded or machined into complicated electrode shapes. Okay, graphite has shown a low tendency to wear. It has the possibility of being molded or machined into complicated electrode shapes. Okay. Next, the wear rate of the electrode tool material WT and the wear ratio RW described by Kalpakjian during 1997. Okay, these two are the formula for WT and RW. What is WT? Electrode tool material. RW is the wear ratio. Right, where WT equal to wear rate of the tool in cubic millimeters to minute. I is the EDM current in amperes. T suffix T melting point of the tool electrode in degree centigrade. T suffix R ratio of the workpiece to tool electrode melting points. Okay, so however the formula is very much important. Okay, About dielectric fluids. The main functions of the dielectric fluids are, first one, flush the electrode particles from the machining gap. Second one, provide insulation between the electrode and the workpiece. Cool the section that was heated by the discharging effect. Okay, let me repeat. First one, flush the eroded particles from the machining gap. Okay, so the dielectric fluid medium is constantly circulating and flowing between the machining gap so that the removed or eroded particles will have to flush out. Okay, for that this dielectric fluid will help to flush it. Second one, insulation between the electrode and the workpiece. Already we have discussed that there would be a spark between the tool and the workpiece to remove the or to erode the workpiece. Okay, so obviously there must be an insulation provided or there must be a shielding around the tool and the workpiece. Okay, for that the dielectric fluidium is helping. Third one, cool the section that was heated by the discharging effect. So obviously dielectric fluid medium will cool the nearest zone of melting. Okay, the heat affected zone should not be affected because of the thermal effects so that it will damage. So the dielectric fluid medium will cool that section or zone. Okay, heat affected zone. Okay, right. The main requirements of the EDM dielectric fluids. Okay, first one, adequate viscosity, high flash point, good oxidation stability, minimum order, low cost, good electrical discharge. So these are the main requirements of the dielectric fluids. Okay, so if there is no adequate viscosity, the fluid flow will not be cooperate to flushing out the eroded particles from the workpiece and the electrode. Okay, so it must have high flash point and good oxidation stability, and there should not be harmful effects to the operators. So minimum order and low cost, and it must be a good electrical discharge. Okay, right. So these are the references. Next we will see the other material removal mechanisms. Thank you.
Like, share and subscribe. Hit the bell icon for more updates.